I want to cover a couple of the other kinds of transitions so that you understand them, and then with that foundation, move on to electronic transitions. So first of all, to understand electronic transitions, you kind of got to understand the size of a photon is comparable to the size of a molecule, the charge distribution of a molecule. And so when a photon hits a molecule, it kind of hits that whole charge distribution at the same time. Real quick, the description of a photon, we've got this oscillating sinusoidal curve, and that curve communicates oscillating fields in space, right? So at one point in time, or in space and time, you've got a field here that's pointed in one direction, right? It's an electromagnetic field. Important to remember that that field is going to have exactly reverse effects on a positive charge and a negative charge. The forces that it exerts on a positive charge are going to be equal and opposite to the forces it exerts on a negative charge, right? It's an electromagnetic field. So this field is oscillating in space, and it's hitting a molecule. Down here, I gave you a little example of how you could generate an electromagnetic field. I told the kids in lab that a field essentially is created by the movement of charge. Maybe I said this in lecture too. So I said you put a charge on a stick, you make it move around, it's going to generate these oscillating fields, right? And so important to remember, photons are actually generated by the acceleration of charge. So you've got a charge over here in space, and it's moving around, and it's communicating, it's transferring energy to other charges in space, all right? And so we have that. Now, let's try to look at what happens when a photon, let's give some examples of what happens when a photon actually hits a charge distribution, a molecule. We'll get into the energy of light and stuff like that later. I've drawn a couple pictures here. One is, and I'm not a great artist, one is supposed to be a molecule rotating, right? That's this guy right here. If you take a molecule that's rotating, it's got some periodicity of its motion, it's moving around in circles, and you hit it with a photon. And also, I'm sorry, this molecule has to be charged. It has to have a separation of charge across the molecule. So I've drawn one end of the molecule being positive, the other end of the molecule being negative. If you hit that with a photon, if the photon is vibrating with the same exact frequency that the molecule is rotating, and if the photon hits in just the correct orientation, it'll cause forces on the positive charge to move in one direction, while forces on the negative charge move in the opposite direction. So it's like you give that little rotating molecule an extra spin. Just put some torque on it. Now it starts spinning faster. Effectively, what's happened then is that the energy that was carried through space by that photon gets turned into kinetic energy of the rotations of that charged species. All right, so that's rotational excitation. Down here, again, I'm not a good artist, but this is vibrational excitation. So now let's say that we've got a molecule that's vibrating, and the molecule has charges, positive end and a negative end, and the vibration is such that those charges are moving as the molecule vibrates. Now we're going to hit that molecule with a photon, and if the photon has the same frequency as the vibrational frequency of that molecule, and if it hits in the exact correct orientation, you can imagine that when the photon hits, it'll cause equal and opposite forces on the positive charge and the negative charge. So maybe it pulls the positive charge and negative charge out for one instant in time. But then as the photon changes its, whatever it is, position, it'll change those forces and squeeze it in. Right? The photon oscillates with time. So one moment, the forces from the photon are pulling the charge, positive charge and negative charge away from each other, but as the photon goes through its cycle, at some other instant in time, it starts pushing back together. Well, what happens if you take a spring and you stretch it out and then slam it back together? It starts vibrating with a larger amplitude, right? And so because you had that vibrating charge separation in space, and because a photon exerts fields on charged species, that photon's energy got delivered to the vibrations. The energy that was stored in the photon became the vibrational energy of the molecule. Now this is stuff we don't talk about in Gen Chem, but I'm trying to get you guys to that whole thing where it's all about charge and interaction of charged species and light and matter and all that stuff. And so I wanted you to see this. Here's the stuff that we're more familiar with. The electronic transitions. We already talked about electronic transitions in lab, for the light and matter lab. We're taking electrons, we're loading to excited states, and then the electrons are falling back down to excited states. So that one's a little bit easier to understand. You got a positive charge in the nucleus, you got a negative charge in the electron distribution, and if a photon hits that charge distribution in just the right way, it can actually promote that electron to a higher energy electric orbital, a higher energy orbital, right? So 3 different kinds of interaction: rotational, vibrational, and the one that means the most to us in the context of this course, electronic excitations. You get those photons, or the photons from one electron out to excited states. Is that too fast? Any questions? Okay. So one of the things that we didn't cover with as much depth as I would have liked to in lab is the Bohr model. And so we're going to go ahead and talk about the Bohr model right now. The Bohr model is really cool. Hydrogen's emission lines were predicted by theory. They were able to come up with, and this was interesting because it's actually very complicated to predict these kinds of things just using the math. But it happens that the hydrogen atom is a very, very simple electronic picture. And so the math that describes it ends up being very simple. And so years and years and years ago, they threw a couple of pieces of math together, and they were able to spit out an equation that predicted the emission spectrum of hydrogen. So we'll get to that here. These notes. So at the first top of this notes, I've done a work problem, and we're gonna go over this problem in a second. But this is what I was talking about. Essentially, they were able to come up with a theory, a mathematical expression that said that the change in energy between 2 positions, 2 orbitals in the hydrogen spectrum, the difference in energy between those, and therefore the energy of a photon emitted, was going to be equal to 2.179 times 10 to the negative 18 joules, this is in units of joules, times 1 over the number of the excited state orbital, or not the excited state orbital, but the initial orbital, minus, or 1 over the final orbital squared. So if this is n initial squared, and that's n final squared, this corresponds to a transition from the hydrogen n equals 4 level to the hydrogen n equals 2 level. So they were able to predict that they could calculate the energy of those transitions using this equation. In this problem, we figure out first what the energy is of a 4 to 2 transition. We turn that into a wavelength. We find out the wavelength is 486 nanometers. We'll get back to that in a second. That was all calculated using the Bohr model. Let's talk about what the Bohr model does, and then we'll get back to the problem. All right, this is cool stuff. Little bit too heady for exam material, but definitely good conceptual material and a good way to introduce you to the hydrogen atom, or not just the hydrogen atom, but some of the postulates of what electron orbitals are and what, I guess, how their energy is stored. A couple things here. What keeps an electron bound to a nucleus? We talked about this sort of, but we didn't talk about it in depth. You got the attractive forces of the proton, right? And they had this problem, the ultraviolet catastrophe, or whatever they called it. There were theorists that said, well, if the electron is attracted to the proton, it's just going to fall right into the nucleus, right, and cease to be. And they couldn't figure out why an electron didn't fall into the nucleus. And then essentially it was proposed or figured out that electrons were in motion. They weren't still particles. They revolved around the nucleus. So if you take a object and you want to, like, maybe you take a rock and you stick it on the end of a rope and you start twirling the rock around. The rock naturally has the tendency to fly, to escape its orbit, right? It's got forces that are pulling it outward. But your rope is providing forces to pull that rock inward, yeah? To keep it attached to the string, to keep it moving in a circle. The electron's doing the same thing. It's moving around in a circle, and because it has this kind of circular orbit around the nucleus, it has this tendency to be pulled away because of that motion. But it's the electric potential of the nucleus that keeps it bound tight. And so for a stable orbital, when they were putting this math together, they said that essentially the attractive forces, the attractive electronic potential, and in the case of the hydrogen atom, that potential looks exactly like our R-squared force law, because it's a spherical distribution of potential around a central charge. So the electrostatic potential energy had to be equal to the energy required to hold that electron in orbit, centripetal acceleration. So we set those two equal to each other. We leave that we leave that up there for a second. Then they said they were starting to figure out that matter could behave as waves. They had electron diffraction that had kind of spooked them. Nobody realized that an electron could be diffracted. They had these experiments showing you that electrons could actually behave as matter. And so from that came the de Broglie relationship, that the wavelength of a particle was equal to h over p. Now h is Planck's constant, p is the momentum of the particle. Momentum is mass times velocity. If we're talking about an electron, we need the electron mass times the electron velocity for the momentum. So that's another little piece of math that they put up there. Lambda is equal to h over p for an electron. I'm going to put that little piece of math in position, and then we're going to make one more assumption. And this was the weird one. And this assumption kind of derived from the whole an electron is a matter wave thing, the de Broglie relationship. And that was that because this electron is being assumed to travel as a wave, its orbit can be restricted, in the case of the hydrogen atom, to circular paths that contain integral numbers of the wavelength. And this is what gives rise to, this piece here gives rise to the quantization of energy in molecules and the orbital structure of hydrogen. So what does this mean? What that means is this. For your hydrogen, you come to think of these as the n equals 1, the n equals 2, the n equals 3 orbital levels, right? So we've got n equals 1, n equals 2, n equals 3. The distance of this orbital, 2 pi r, 2 pi times the radius, right here, has to be equal to an integer times the wavelength of the photon. We know that the wavelength of the photon is h over p, h over the momentum, right? So that's right there. The orbital restrictions were such that for n equals 1 level, one wavelength of, I don't even know how to draw, of a photon had to fit around that circle. That's a shit drawing. I'll draw another one that's better. So at the n equals 3 level, that looks like this. You've got a max amplitude of the wavelength here. It comes through here. It achieves maximum again right here. Comes back down. Achieves maximum height over here. And then comes back down into there. So you end up with this 3 complete wave cycles being gone through as this photon takes a path from one side of the orbit to the other. And the n equals 2 would be 2 complete waveforms, etc. So what they were, it's weird stuff, but with these assumptions that the orbit had to be distances that were equivalent to integral numbers of wavelengths, and with the assumption that the electron behaved as a matter wave, where it had a wavelength, h over p, and with the assumption that that you had to have those electric forces and those acceleration forces be in balance in order to have the electron bound, they went and they put all of this stuff together and derived that equation that I showed you at the start. That number, really, or that relationship between the energy and the principal quantum numbers. So remember, that's n equals 1, n equals 2, n equals 3. That energy equation that we had up there, we had 1 over n initial minus 1 over n final. The n's are those quantum numbers for the different orbital levels. Let's see here. So I'm going to leave this as a problem for you, an extra credit problem, not what's on the screen right now, but this part up here. So if you can take these 3 statements and then turn them into the resulting equation, which is this one right here, you'll end up with all your constants globbed together in a chunk that looks like this. You plug in all the values for the electron mass and the electric charge and permittivity of free space and the Planck's constant, etc. And you pull out the n squared, you get this 2.179 times 10 to the negative 18. That sits right in front of the 1 over n initial minus 1 over n final, and that equation you can use to calculate the energies of the transitions. So I'm offering extra credit for moving from what's at the top of that page to what's at the bottom of the page. So there's a bunch of algebra in between. It's only algebra. There's a lot of variables to juggle, and you're going to have to do some cancellation and stuff like that. But I imagine if you gave me a good write-up, you might be able to get as much as 10 points extra credit for. All right. So we make all those assumptions, put together this equation, and we can then take that equation and use it for calculations such as that one at the top. So let me just dig up a picture of the hydrogen spectrum real quick. That's the guy. That is not the guy. That is not the guy. No, that is not it. Oh, so this set of slides right now are Jane's slides that are relevant to this discussion. This is not the one she has hydrogen in. Where she got the hydrogen spectrum? There we go. So there, right here in this bottom picture, is your hydrogen spectrum. Your 486 line is just inside of 500 right there. That's the one I calculated. It would be good practice for you guys to go in and calculate some of these other lines. There's a couple that are below. They're like at 420, 430. These are the blue lines that we saw on the hydrogen spectrum. Over there, we've got the red that's like at 680 something. All of those wavelengths can be predicted by plugging in the appropriate initial and final orbitals for the hydrogen. It turns out that the visible spectrum, the visible lights that you get in the hydrogen emission spectrum, correspond to energy transitions between higher levels and the n equals 2. So if you select your n equals 2 to be your final level, so you got 1 over n initial squared minus 1 over n final squared. If you select n equals 2 to be the final, and then you simply adjust the n initial to be 3, 4, 5, 6, etc., and you do the calculation correctly, you'll be able to calculate all of those wavelengths that we show right here. The 480, or the 686, the 486, whatever they are. I'd encourage you to go in and do a couple of those, just for the sake of verifying that that's doable.
Back to our show.
Another thing that I didn't say in the lab as point I didn't make as clearly as I would have liked to, as I wanted to, was the difference between continuous absorption spectrum, or continuous emission spectrum, and discrete is what the other word is, discrete emission. So in the hydrogen atom, we've only got a few orbitals available. And so there's only a few different transitions that can happen. And part of the reason for this is because hydrogen is a very, very simple system, and you have only got one nucleus and one electron interacting. We've shown you a bunch of different times the orbital structure for hydrogen, the n equals 1, n equals 2, n equals 3, etc. When you start putting more electrons and more nuclei together, and you build molecular systems that have multiple electrons and multiple nuclei, effectively what happens is you obtain more different orbitals or states that are available for the electron to be in. So if your hydrogen spectrum looked like this, where you've only got n equals 1, n equals 2, n equals 3, an orbital diagram or whatever for a larger size molecular system, charge system, might look like this, where you've got a bunch of orbitals, a bunch of different possible electron positions, energy levels available for that electron. And so instead of just having a couple of different transitions between 5, 6 different levels, now you've got the ability to have dozens and dozens of different possible transitions because you've got so many stinking different energy levels available. That translates into absorption spectrum. The absorption spectrum of continuous. We saw a bunch of continuous absorption spectra in lab, right? Where you didn't have just a couple of different lines. You had peaks that blended together and looked like this bell curves or whatever they were. So when the electronic structure becomes more complex, more energy levels become available, therefore you have more transitions between different levels, and you have a spectrum that becomes continuous emission instead of discrete emission. Okay. All right. When we were talking about conductivity, I forget if it was Thursday or Tuesday or what day it was, but when we were talking about the different kinds of bonds, we showed you metallic bonding, ionic bonding, covalent bonding. We said that in metallic bonding, the electrons were held so loosely that they just kind of move about freely, and that's why metals are conductors. Ions, it turns out, conduct electricity when they're dissolved in solution, but they don't conduct electricity in the solid. We said that covalently bound substances. So what a covalently bound substance is it's either an entire solid that's linked by covalent bonds. In fact, that's just what we'll call it right now. So we'll look at solid silicon. In covalently bound silicon, you've got a bunch of silicon atoms that are linked together by covalent bonds. This covalent bonding extends kind of through the solid, and you get this piece of condensed matter that doesn't conduct electricity, largely because silicon is non-metallic in behavior, which means it's towards the right-hand side of the periodic table and it holds onto its electrons very tightly. Remember we said as we go to the right-hand side of the periodic table, the atomic radius decreases, therefore the electronegativity is increasing. Well, silicon is one of those guys that has a high electronegativity. So it tends to hold on to electrons kind of very tightly. It doesn't let them move around. And we'll also find out that there's something about its bonding structure that, that kind of causes electrons to not be mobile in that substance. You can treat silicon in ways that make it conductive. Regular pure silicon will not conduct electricity. You take a battery, you stick it at either end, you're going to have to really ramp up those potentials if you want current to flow. And by the time you get potentials high enough, the material will be destroyed. So silicon is not a good conductor. If you add things, dopants, minority kind of particles into this silicon material that have either more or less valence electrons than silicon, you'll cause this material to begin to conduct. So, hard to explain. Let's give a for instance here. Good slide right here. So silicon has 4 valence electrons. Yeah. Now, in the covalent solid, silicon's going to try to share these 4 electrons with some other species. It's going to make covalent bond, or if the case is that we've got another silicon atom, it's going to make a covalent bond. 2 silicons are going to get together. And they're going to share these 2 electrons. You'll have another silicon over here, and it's going to share those 2 electrons. You'll have another silicon over here, it will share these 2 electrons, and those 2 electrons. At this point, through sharing, this central silicon that we started with feels like it has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outside valence shell. Yeah? How many spaces for electrons does the silicon have in its outside valence shell? Let's grab a periodic table real quick here. Silicon is built as we are filling the n=3 level, right? So we're in that 3rd valence shell, we're starting to dump electrons in there. Silicon comes with 4 electrons, but there's room for 4 more electrons in that valence shell, correct? So by having these 4 bonding interactions, this silicon has put 8 electrons in that valence shell. So that valence shell is filled. This is the kind of bonding that silicon has in solid silicon. It's got covalent bonds. It's filled its valence, its lowest shell available with electrons. Negative type doping, N-type doping, consists of taking material that is largely kind of this tetravalent silicon and adding dopant species into the structure that have 1 additional electron. Negative, it's called N-type doping because that additional electron is negative. Phosphorus will do that. If you take silicon and you replace every once in a while, you replace this position with a phosphorus. This phosphorus atom had the 4 valence electrons plus 1. It had 5 valence electrons. It can make this bonding arrangement, but after it does so, it's got 1 electron that's left over that can't be shared. Here's the story. we just closed that N equals 3 valence shell, right? All the bulk material behaves like silicon. The N equals 3 valence shell is full. There's no room for electrons in that shell. But we've got an extra electron because we put that phosphorus in there that came with 5 valence electrons. That electron has to go somewhere. If it can't go in the N equals 3 level, or